My name's Clay Jones. Today I'll be talking to you about the geology of the Utah Forge Enhanced Geothermal System. Utah Forge is a dedicated underground field laboratory sponsored by the U.S. Department of Energy, where scientists and engineers are working to build a fractured geothermal reservoir in hot, dry rocks. Utah Forge is located in southwestern Utah. Its location shown by the star here. Below that is a geologic map. In geologic maps, each colored polygon represents the extent of a different rock or sediment on the Earth's surface. So in this map, the brightly colored polygons on the right hand are rocks exposed in the mineral mountains. The shades of tans and yellows on the left, where the Utah Forge site sits, outlined in red, are all sediments of the basin. So in the mineral range, we have plutonic rock shown in greens, oranges, and blues. Those range in age from 25 to 10 million years old. And also on the western flank of the range are some 1.7 billion year old Precambrian metamorphic rocks in gray. And on top of the range, shown in purples and pinks, are rhyolite domes that are about half to 3/4 of a million years old. Here are some examples of outcrops in the mineral range. See some plutonic rocks at the top, different kinds of granites. Some more examples on the bottom left and bottom right. And we have a bit of a close-up here of some banded metamorphic rock in the lower center. On the right-hand side of this slide is a cross-section through the Utah Forge site. This is a vertical plane giving a view of the Earth's interior as if it were sliced open. That slice is happening along this pink line. So you split your cake, pull it apart, and look at the layers. Also in this figure are the wells that have been drilled as part of Utah Forge. Here is our injection production deviated pair in blue and red. We also have some deep vertical wells. The cross-section also has temperature contours, showing the depth at which temperatures of 175, or about 350 F, and 225, or about 450 F, are reached. We are working on building our fractured reservoir between these two temperature contours. So with depth, these wells drill through the basin fill of various thickness. It's getting thicker out here to the left. They hit the top of the basement, which is sloped, and marked by sheared and altered rhyolite and sheared and altered granitoid, before getting into less fractured and less altered rock below. The granitoid is pretty variable in composition. It ranges from diorite to granite, and the deepest part of the reservoir, we get into a mixture of granitoid and metamorphic rocks. The metamorphic rocks are mostly orthogneisses, which means they're deformed granites with compositions very similar to the granitoids. A little bit of slimonite and a little bit of garnet here and there, but for the most part, they're quite similar. They're also isolated, rare occurrence of marbles, schists, and quartzite, but those are generally pretty thin with drill intercepts ranging from tens to hundreds of feet. Utah Forge is located within the Basin and Range, a region of extension and crustal thinning accommodated by normal faulting. So let's run through the tectonic history here, starting with the oldest and working our way to present day. So in the first panel, we're showing blocks of fractured rock, that's the diamond pattern, intruded by younger dikes, the vertical lines. In the next panel, with continued extension, one of these fracture zones coalesces into a brittle normal fault in the upper crust, with plastic deformation in the lower ductile crust. This transition is usually at about 400 degrees Celsius. Jumping along to present day, the cross-section we looked at on the previous slide was within this blue box. Top to the east rotation tilts the vertical dikes and changes the dip of the fault zone, which is now dipping at 25 to 30 degrees, instead of steeply dipping as it was back here. It's also brought some of the plastically deformed rock up near the surface, and now the fault zone reorients itself to a steeply dipping geometry where it's able to break and slip. Here are the type of analyses that provide the images and data that we'll be looking at. In optical petrography, Plane or cross-polarized light is shown through very thin slices of rock, typically about 30 microns. In X-ray diffraction, powdered rock is loaded into this device. X-rays are shot at it at different angles. It measures the spaces between planes of atoms and crystal lattices, and from that data, we can determine what minerals are in there and the proportions of those minerals. We looked at the rocks with a scanning electron microscope equipped with an energy dispersive spectroscopy unit. So in these backscatter images, which are mostly what we'll be looking at, elements with higher Z values that are further down on the periodic table have bigger nucleuses. Those bounce more electrons back at the detector, so those appear to be lighter in color. And also, while this is all happening, some of the inner electrons get knocked out of their orbitals in these atoms. Ones from higher energy outer orbitals fall in, release an X-ray. Those X-rays are characteristic of the configuration of the atoms, so you can tell what elements are in there. Rock samples that come from within our reservoir are retrieved during drilling. So we have a drill rig here, set up at the forge site. It's going to send its bit down on a pipe up to a couple miles long. Here's some different types of drill bits that we've used. This PDC bit has been the most effective by far. It's really got us cutting through this granite at up to a couple hundred feet per hour, but it makes the tiniest cuttings. Here's a picture of some cuttings we've retrieved and a 0.5 millimeter pencil lead for scale. As you can see, they're a couple millimeters across max. The rock fabric is totally obliterated, but it gives us a sample of what's down there, and with a lot of effort, we can put Humpty Dumpty back together again. Some more examples of some cuttings. So cuttings are collected every 10 feet. So we know the weight we're pumping down, we know the volumes of everything, we can time it and grab a sample off the shakers that represent cuttings roughly every 10 feet. On the left-hand side, we have all of the cuttings from well 5832. It was the first well we drilled out there, down to about 7,500 feet deep. And on the right-hand side, we have lithologic columns, which have pictures of the cuttings collected every 10 feet draped on top of them. So we have our deviated injection well here and a few of our deep vertical wells. You can see some hematite staining in the basin fill before we start getting into the granitoids of various composition. And that really shows up here by the presence or absence of ferromagnesium phases like biotite or hornblende that will just make it a lot darker. And then down in here, we start to get into our metamorphic rocks and plutonic rocks that are mixed together. Here we're looking at lithologic columns constructed from pictures of the cuttings from several wells and different rock type units as colored blocks. And over here on 16A, I've divided things up into vertical, curve, and tangent sections of the well. What I'd really like you to look at are these XRD data sets. So it goes from 0 to 100 weight % of the sample, and they're color coded by mineralogy. We've got quartz in red, potassium feldspar in green, plagioclase feldspar in yellow, and all other primary minerals. This is going to be dominantly biotite, hornblende, titanite, and magnetite in dark gray, and then secondary or alteration minerals. Minerals formed by water rock interactions or minerals that are filling veins in the rock in pink. So you can see that the vast majority of the subsurface at Utah Forge is composed of quartz, plagioclase, and potassium feldspar. And if you include all the primary phases, it's greater than 90%, probably for all but a few samples. There's a bit of increased alteration near the top of the basement, where it is fractured, and a couple of other places at depth, where we hit fracture zones where alteration occurs and fractures have been filled by secondary phases. Let's talk about how plutonic rocks are classified. To do this, we use ternary diagrams that plot three variables: the normalized abundances of quartz, Q, alkali or potassium feldspar, A, and plagioclase feldspar, P. So if a sample is 100% quartz or dominantly quartz, like this fellow up here, it plots near the apex of the pyramid. If it has very little quartz, it plots down here, near the bottom of the period. The fields underneath are different rock types. You can see that most samples plot in an L-shaped trend running from granite down to the bottom, then over to diorite in the plagioclase-rich corner. So these symbols are color-coded by depth, going from shallow in purple to deep in red. There is a compositional shift away from the K feldspar corner at the deepest drilled levels that you can see in the orange and red points in 78B32, 5632, and 16A. If we look at 16A, our injection well, you can see that as we move deeper to depths below 8,000 feet, things shift out to the right. Similar compositions are also observed in some wells drilled to the east of the forge site in and around Roosevelt Hot Springs hydrothermal system. Interestingly, this compositional shift with depth is not observed in 16B, which is only about 300 feet vertically above 16A. I guess the takeaway here is that there's a lot of variability in the flavor of granitoid we're hitting in the reservoir. Okay, cross sections again. We're going to go oil and gas versus geothermal. Oil and gas, you're going to be in a sedimentary basin. You're probably going to be drilling through horizontal layers of rock. You're going to go from youngest to oldest. Drill down, hit your pay zone, go horizontal. Everyone's happy. You drill an offset well over here, you're going to largely hit the same layers. We move over to Utah Forge. We know we got to get through this crunchy topping, but once you get down through that, it's kind of anyone's guess. We see variability in plutonic rock composition over various scales. It's pretty challenging, at least in the cuttings, to differentiate plastically deformed metamorphic rocks, and I'll show some examples of this in a minute from the plutonic rocks. And it's really surprising how different the rocks are, even between our injection and production doublet that are only 300 feet apart. Physical logs were obtained by tools that were run in and out of the hole before the casing pipe was installed. This is an example of a micro-resistivity log. This particular tool has pads that are on springs that go out, touch the borehole walls, and measure how resistive they are. This log from well 5832 goes through the alluvium, into the sheared granite, then down in the different flavors of granite. In the static image log, we see dark colors which indicate that it's conductive. So in the basin fill, there are pore spaces between the clasts full of conductive salty fluid. Then we get into the sheer top of basement. It's maybe even more conductive, with salty fluid filling fractures. And then as the fractures die out and porosity declines, the rocks get lighter and lighter, less resistive with depth. We can also take a look at the fracture distribution. Fractures full of salt water or even the drilling mud are more conductive. We can see that there is a lot of fracturing at the top of the basement next to the abandoned fault surface and then diminish with depth. Here are some more geophysical logs from well 5832. Same one we just looked at, alluvium, sheared top of granite, different types of granite. We've got gamma ray, which is how radioactive the rocks are, travel time, how quickly sound moves through the rocks, the density of the rocks, the pores in the rocks, so how much space is filled by water, and resistivity, which is just sort of an expression of that colorful log we just saw. So we can see big changes here as we move from the alluvium into the sheared top of granite. And then by the time you get to the bottom of that, everything sort of levels out and normalizes, at least in these three logs. There is there's more change in the gamma ray due to the particular composition of that rock, whether it has more potassium, feldspar, biotite, whatever have you. Potassium is going to be a big contribution to this. Here we have the spectral gamma ray log from well 16A. This log measures the natural radiation emitted by the rocks. In this log, we have the total gamma radiation as well as its various sources with contributions from potassium, thorium, and uranium. The gamma log data is plotted against XRD data from 100-foot intervals, showing the abundances of potassium-bearing minerals, potassium feldspar in green, biotite in black, and illite in blue. And what I'd like to point out here is as you're coming down, the potassium is really variable, but high. And as we get down to 8,000 feet, which is where the granitoid plus granitoid and metamorphic rocks meet each other, it's also where there's a pretty good fracture zone. You get a big drop in potassium across the contact. That also shows up in the XRD data. It's masked a little bit in the overall radiation or gamma log by increases in thorium and uranium. We've talked about drill cuttings, now let's talk about core. This golden donut is a coring bit. Send that down the hole and whatever goes into the center here, like these cylinders of rock, are what's brought back to the surface. We can get up to about 30 feet at a time in the configurations we've used. And then I wanted to show you this picture because we're going to be looking at quite a few of these. These are flat images of the entire 360-degree circumference of the core. Images were taken at different angles and stitched together so that you can see the entire exterior of the core at once. We have an abundance of cutting samples from all wells. They're collected every 10 feet, but not nearly as much core. It's quite expensive to get. Here I'm showing the trajectory of 16B, and these thin discs represent depths over which core was taken. The core is shown here over the right-hand side. So we grabbed a core here in the shallow vertical section. That's this nice white one over here. And then we jumped down to near the toe, where we cored through zones which we had previously stimulated, looking for the fractures that we made. So the first dark color is from the stimulation number 3. We jumped down about 400 feet to get to this light colored granite, jump down another 200 feet, and we're back in this dark metamorphic rock. First 2 core runs we did were in the pilot well 5832. We sent the bit down, got about 10 feet of this flavor of granite, brought it back up to the surface, drilled ahead, cored again, and this time we caught 2 different rock types. You can see this banded, finer grained, darker rock, and then back into a more granitic rock. These have been age dated at 12 and 22 million years. So this is a younger dike that was intruded into a fracture in this older rock. And then over here we have backscatter SEM photomosaic maps. Now this is a 5 millimeter scale bar. This is a 1.5 inch plug. So it's composed of many small images that give you a good idea what the texture of the rock is. You can see some banding in here. You can also see that it's a lot finer grained, a lot more staticky looking than this rock down here, which comes from this section, the wall rock that was intruded. This is an example of a metamorphic lithology, an orthogneiss, or plastically deformed granitoid with a modified rock fabric. This sample comes from about 8,500 feet below the surface in 78B32. On the right is a core piece that has been cut in half and polished. From within this yellow box, a large thin section was made with a black and white backscatter image of the thin section at center. This is a 5 millimeter scale. At right are photomicrographs of the thin section in plane and cross-polarized light. You can see there's quite a bit of texture here. that's the result of ductile plastic deformation under strain at high temperatures. Algans are these ice-shaped features. They are white and pink potassium feldspars in the core slab photo and are the large gray blocks in the middle SEM image. And a fine-grained myelinite, the dark band in the core photo, which has a lot of biotite in it. Biotite is iron and magnesium bearing, so it's a little bit heavier on the periodic table and a little bit lighter in the SEM image. Shearing at high temperature results in grain size reduction as smaller mineral grains fall off the larger grains. It's unclear how much displacement has been accommodated by the myelinite, but it could be significant. This core comes from 5,495 feet in well 16A, and we've cut two thin sections at two perpendicular orientations, one horizontal and one vertical, and you can see the rock fabrics here in the different orientations. This one's got a nice foliation to it with stringers of quartz and biotite stretched between rounded feldspar grains. This sample comes from near the toe of 16A at 10,961.6 feet, also shown in two orientations at center. In these SEM images, you can see the dark colored, coarser grained veinner dike that has been folded. That's the white colored line in the exterior core photo. And over here in the photomicrographs, you can see biotite in dark shades, black to green in the upper image, and as colorful grains in the lower image. And quartz and feldspar are transparent in the upper image and show up as shades of gray in the lower image under cross-polarized light. Here are images from another coarse sample from near the toe of 16A that are a different flavor of metamorphic rock. This has some really regular banding, kind of looks like sinusoids here when you unroll it. And here we see a biotite band cutting through. These are the dark layers here. And just the inverse of that, the biotite bands are the light layers in the SEM photomosaic. To form in either a brittle or ductile fashion. This is a function of temperature and also strain. What I'm showing here are images of a myelinite. This is a very deformed zone that has accommodated a lot of strain with drastic grain size reduction. So with increasing temperature, biotite is the first mineral to start getting squishy. Move up to about 250 degrees and quartz will start to deform. Move up to 375, 400, and feldspar will start to deform. So in this image, let's kind of break it down by grayscale. Darkest is quartz, second darkest is plagioclase feldspar, lightest gray is potassium feldspar, and the almost white bits are biotite and other heavy phases. So you can see all the phases have been deformed. You can especially see it in the quartz and K feldspars. But there are also these rounded plagioclase feldspar blocks that didn't quite break all the way down. They were just kind of rolled in the fabric as it sheared. Fractures filled with secondary mineralization are the most abundant at the top of basement and decrease with depth. They are generally thin. The thickest vein we've come across in core is about 1 centimeter across. Most are on the order of 1 millimeter, like the one shown in this picture. There are 5 of them cutting this piece, all sealed and unbroken. You can see their locations on this other image. And these fractures have been filled with secondary minerals over geologic time, from early actinolite, epidote, and albite to later interlayered clays and halite. So on this figure, I've got different minerals plotted against their expected temperature of formation in geothermal systems. Our reservoir ranges from about 225 C to 175 or less as you move up hole. That's the orange colored box. We shouldn't be forming any actinolite, epidote, or albite today. These probably formed at greater temperature and depth before these rocks were brought closer to the surface. What minerals do make sense in our temperature regime now are interlayered clays. So C/S, chlorite smectite. You can also see it filling this vein over here in the photomicrographs, and illite smectite. So this vein was filled first by chlorite smectite, then this thin strand of illite smectite goes down the vein, and it was broken for a third time. So from the same photomicrographs as the last slide, a piece of the core was broken off. This is its rough surface, stuck under the SEM, and this is an image of that fractured rough surface. What you see here is part of a hexagonal clay mineral on its side. They're kind of shaped like plates. And this furry stuff are those same clay minerals on end. And then there are some lighter features in here. This cubic one is a good example. So what are these? Well, we throw it under the SEM and we look at what elements are in each pixel here. So it's going to go across, color the pixels by element. Here they all are together, and here are individual maps. And down here are the two to pay attention to, chlorine and sodium. Halite, table salt, is falling out of these veins and is intermixed with minerals we would expect at modern temperatures, so they were probably pretty young. And these have to be deposited by a pretty darn salty water that was moving through these fractures. That wraps things up. Thanks for joining me. Funding for the Utah Forge project comes from the U.S. Department of Energy, with additional support from the University of Utah, Utah Trust Lands, Beaver County, and the Governor's Office of Energy Development. If you are interested in more information about geothermal technologies in Utah Forge, please visit our website at utahforge.com.